So all those poor kids around the world with no code camp to go to, and you guys are part of the lucky few to have code camps. Welcome. So this is going to focus in on the topics from the IB syllabus that are higher level programming. So if you take a look at the assessment statements page, you got resource management and control, but those are theoretical. The programming higher level is going to be this, and it's going to be the higher level of the OOP. Now the one thing that I do want to show you before we get started is why it's going to be important even for standard level people to know a little bit of higher level. So I'm going to go to the dossier, and I'm going to go to my guide and into the actual programming part and development. If I look at the IB description and rubric and the numbers that are associated with it, if you look at the 9 through 12, this is for both standard and higher level. It says the use of techniques demonstrate a high level of complexity and ingenuity in addressing the scenario identified in criteria A. This does not say a high level of complexity and ingenuity for the SL content or for the HL content. It just says this. And so this is the argument a couple of years ago when all the IB teachers got together. Could a standard level kid reach a 12? And really, theoretically, no. So that's why even if you're standard level, you should include a couple of these things. So let's look at this further. It says it is characterized by the appropriate use of existing tools. That's going to be important with what I do today, because you could use your own linked list, make your own linked list, but that would be a waste because there's an existing tool that we've already looked at called linked list. The techniques are adequate for the task and their use is explained. All sources are identified. So basically it's this. You want to throw in a couple of things that are going to bump your dossier up to a high level of complexity. So we'll get back to the assessment statements. And we'll start in with abstract data structures. So basically at 5.1, which is abstract data structures, and that's it. But it includes thinking recursively, and this is the thing that's a little bit hard to get your head around. Okay, so watch this to begin with, and you'll understand why after we watch it.
There was an old lady who swallowed a fly, by Sims Tabak. There was an old lady who swallowed a fly.
Do you know this one? No?
I don't know
Sorry?
why she swallowed the fly. Perhaps she'll die.
I think I'll cry. But it's only a fly.
Oh my.
She gulped it out of the sky.
There was an old lady who swallowed a spider. It wiggled and jiggled and tickled inside her. She swallowed the spider to catch the fly. I don't know why she swallowed the fly. Perhaps she'll die.
Go on to the by and by.
There was an old lady who swallowed a bird.
So the question is, why did she swallow the bird? That's right. And why did she swallow the spider? That's right. Why did she catch the fly? Or why did she swallow the fly? We don't know. We don't know why. So recursive problem solving is any situation where you solve a bigger problem by solving a similar, smaller problem. And you keep on going, drilling down deeper and deeper and deeper and deeper and deeper until you get to the fundamental case, and then you can work your way back. So she's going to swallow a bird to catch the spider, and then she's going to swallow a cat to catch the bird, and then a dog to catch the, and so on and so on and so on. And so you're solving this big problem by drilling down one level at a time with a similar problem. And I don't think we can quite understand this yet. But what we can do is do the simplest of all recursive algorithms back in NetBeans. So we'll go to NetBeans, and we'll do a new project, and we'll call the project code camp day 1. And we'll just do this in a non-GUI environment. And we're going to do a basic for loop first of all. So let's loop something 10 times. Okay. This is an iterative solution to repeating something 10 times. So when I play this, it will repeat 10 times. This is the iterative solution. So I'm going to put up here. To repeating something, I'll even put to repeating 10 times. Now the recursive solution will look as follows. So the term is recursion. We're going to have an int. We'll call it, well, we can call it I because we're outside of the braces up there. So int I is assigned 0. And we're going to call recursive loop. And it's going to be a method that we're going to create down below. Sorry, I didn't mean to do those braces. Recursive loop. So down after the main, we're going to do a function, public static void recursive loop. Now, that is going to have to take something in. So what we're going to take in will be our I. So int I. And we're going to say if I is less than 10, recursive loop, same spelling, I. But then inside this call, someplace, we're going to go I plus plus. Up here, we're going to send our I. Recursive loop. And so what should happen? We're sending 0. So I is going to be 0. I goes up by 1. Maybe I should have done that. You could do the same thing. Let's put that at the end. And we're going to say if I is less than 10, which it will be, we're going to call recursive loop again. Oh shoot. Let's put it inside. Let's put this inside. Eventually it's going to stop. Now we're not printing out anything, so maybe we should print out right here. Let's go sout I. So without thinking too deeply, let me just see if this is going to work. And we'll put just a sout of a line between these two. And if it doesn't work, that'll give us something to think about, but it works fine. 0 through 9, 0 through 9. So both of those accomplish exactly the same thing. So the question is why? If you trace through it, I could do it in paper, but for the video, let's just see if we can do it in our minds. Send an I, which is 0. Is I less than 10? Yes. Print it out, 0. I goes up to 1. And we send recursive loop 1. So there's going to be another instance of this. Picture two distinct instances of recursive loop. The second one is going to take in an I of 1. Is 1 less than 10? Yes. Print it out. I goes up to 2. Called again. And so on and so on and so on. And sooner or later, I is going to be 9. And when an instance of the recursive loop takes in a 9, if I is less than 10, print it out. Why don't we put else return? That shouldn't change anything, but it'll make it more appropriate. if I were to do this in Photoshop, let me just try this, and if it works, it works. If it doesn't, it doesn't. And I'll do it on paper for you guys. So the thing is, there are going to be multiple versions of this recursive loop in memory. So I'll just draw it with a paintbrush. And I'll just call this recursive loop like RL. So the very first time we have this RL, so RL of 0. In the middle of its call, recursive loop of 0, we make another call. We make another call of RL of 1. Okay? And in the middle of that call, so these are two entirely different things. This is in memory, and this is in memory. Two different things in memory. We might have other things in memory as well, you know, BR or an int or whatever, other things in memory, but these will be in memory. And in the middle of this call, okay, of 1 is 1 less than 10, yes. We print out 1, 1 goes up to 2, we do another recursive loop, this time the recursive loop of 2. And the recursive loop of 1 gets interrupted. And we keep on going, dot, 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 until ultimately we're going to have a call of recursive loop of 10. And when we get to this one, we ask if I is less than 10. Is I less than 10? No. So we don't do any of this stuff. What we do is we return. So that will take this off of what is effectively a stack. And since it's finished, the one before that will be finished. And since it's finished, the one before that, and so on and so on and so on, and we're going to, as we're going down through that stack, this and this and this and this and this, finishing off one at a time until we get to the very first one. And the very first one, that very first recursive call to recursive loop of 0, it will have finished calling recursive loop of 1. It'll get down here and it'll finish, and then all of them will be finished. And so effectively what we've accomplished is we have repeated 10 times by making 10 calls to 10 different instances of this recursive loop. And that's important to realize that each one of these is an instance. We talk about instances of like turtles and basketball games and whatever. Well, each one of these are instances, all the way down through 10 instances. They get basically stacked up, and then one at a time they get resolved until we get back to the beginning. Yep. So the thing is, there are just some situations which are more elegantly resolved this way. If we were to do it in an iterative way, we'd have lines and lines and lines of code, and we wouldn't really be able to follow it. And so with a shorter number of lines of code that we could possibly have by doing an iterative or kind of a series, 1, 2, 3, 4, 5 lines of code for each situation. So it would be 5 times 6. But what if we had an iterative situation that went on 1,000,000 times? Then we'd have 1,000,000 times 6 lines of code. Whereas we can do it all within this kind of a structure and 8 or 10 lines. And there aren't very many situations in the world which act this way, but there are some. Fractals is the classic example that's often given. So let's go back and just see, skimming through this. It'd be really nice if we could get this going. There we go. Okay, it's not working. So I'm going to try this one with you. So ask me where my house is. Andru, I forget how to say this. Andrian Soharanana. And then you say, where is Andrian Sanana? And I say it's in Nalamaitsi. You say Nalamaitsi, it's in Antananarivo. It's in Madagascar. It's a big island off of the coast of Africa. So now you know, because you know the answer to Madagascar, so now you can determine where this roux is. Because in Madagascar, in the capital city, Antananarivo, in the suburb, which I actually did live in, called Nalamaitsi, there was a roux a road called that, and that's where I lived. So by keeping on asking that where is question, you don't get an answer. Like you ask the question, where is your house? And I tell you, but you really don't know. So you have to ask it again, and you do the same function with this new unknown piece of information, and you get another unknown piece of information, but you call the same function with that and the same function with its answer, and sooner or later you're going to drill down, you're going to get to something that is resolved, something that makes sense to you, and because that makes sense to you, everything else then falls into line and makes sense to you. That's the thing with recursion, is the first time through you don't get satisfaction, right? Because in the middle of doing something you don't finish, rather you keep on going. You keep on going with another instance of the same thing. But sooner or later, you're going to end up to the return. And thereby you repeat. Okay. This is from the old textbook that I used to use, a university textbook. And it's going to show you how the order in which you do things in a recursive method really make a difference. So here is, there are two different ones. This one, print string, is going to check to see if the length is 0 first and then return. Else, it's going to print out a character, and then it's going to call the same, I can't double click that, it's going to call the same method with a different substring. We call the method print string with hello. We print out the h first, and then we print string the rest of the word, which is going to be substring from 1, and substring from 1 is going to print from 0, 1, from the first through to the end of the word. And so we do see, in terms of the output, the h first before we're interrupted. We're interrupted by this. Okay, we print the particular character, and then we call the recursive function again. So the second recursive call is going to take in ELLO, right? That gets sent to print string. So that's the second instance. This is not quite finished yet. We have a second instance of the method. And what do we print out? We print out the E, and then we call another instance, the third instance of print string, with LLO. So LLO gets sent to the third instance. We print out the L. So you can see that these are going to be printed out in a row, H, E, L, L, O. And eventually we're going to get down to here, and we're going to call a print string of nothing. And when there is a length of nothing sent to the print string method, we just return. So finally, down here at the bottom, this just returns. Since it returns, this instance is finished, and this instance is finished, and this instance is finished, and that are all finished. What we've accomplished is printing out the H, E, L, L, O in order. But if we had reversed the order of these two things, when we were printing and when we were calling the next recursive instance, as we see here, because we called the print reverse before we print out the character, here's what happens. We call the first instance of print reverse with hello, and before we print out the H, we print reverse of the remaining letters. And then we print the print string, or call print string with the remaining letters, remaining letters, remaining letters, remaining letters. We never get to any of these print lines, because before we get to the print line of H, we were interrupted by that. Before we get to the print line of E, we were interrupted by this. We just keep on interrupting, 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 interrupting until there's nothing left being passed on. And so we get down to here, actually, because the length in this case is not greater than 0, so we get to here, which means we're finished this one. If we're finished this one, we go, and this is the key thing, we go back to where we left off. Where we left off was calling this. We're finished this line, which is this. And what's left in this instance of print reverse? Printing out the line, because we still have this line to do. this line was left undone. So the very first thing that is printed out is actually the O, because it was this one which was the result before that one, before that one, before that one, before that one, and there was still stuff left to do. We still needed to print the O, still needed to print the L, and the L, and the E, and the H. And so the order in which they're printed is reverse, O, L, L, E, H. Whereas above, by the time we got to the next call to print string, we had already printed the stuff out. The last classic example of recursion would be this one, of Hanoi recursion. This is the most classic example of recursion, and we're not going to look through the whole thing here, obviously. But without getting into details, because we don't have time, you're trying to move all of the disks in the towers of Hanoi from one side to the other, but the problem is that you can't ever put any larger disk over a smaller disk because it'll break it. And this comes from some ancient Vietnamese legend, whether it's true or not, but the answer was, how do we move all those to here? And we've got these two pegs. And the iterative solution is complex, ununderstandable, and long. The recursive solution is like 3 or 4 lines. And we'll look at the recursive solution, and that'll be it. We'll move on. But if you just watch what's going on here, you'll see that never does any one of the disks that is larger go on a disk that is smaller. And you can only move one at a time as well. So if we looked up this Towers of Hanoi in Java, you'll see that it's short. And this is what we'll get to next when we look at a recursive solution for a binary search. The do towers, the secret is, when you're making the recursive calls, the order in which you send the parameters. Here it's top n minus 1 from to enter, and then it's top n minus 1 enter from to. So the order in which the parameters are sent is going to change very much how it works. And so now we'll take you to an actual implementation that you can use on your dossier.